subscribe now and press the bell icon. Never miss an update.
Good morning, student friends. Again, welcome back to the electrochemistry sessions. Very briefly, I will explain what all I have been taught in the last period. Very fundamental concept I have given to the electrochemical cell, or a galvanic cell. I define galvanic cell is a device which converts chemical energy into electrical energy. So that is called as a galvanic cell or electrochemical cell or radial cell or voltaic cell. So to construct a galvanic cell, I have taken the two electrodes of different reactivity. I have taken one zinc electrode is more active, copper is less reactive. So metal rod is dipped into the metallic salt solution. So there due to the electrical double layer, a potential has been developed. So one becomes the oxidation, one reduction, one becomes anode and cathode. So these two single electrodes are off cell are combined internally by using a salt bridge to give the electrical contact between the two off cells and current externally through the copper wire. We can see the current flows in the outer circuit. And what is the direction flow of current going to be going from the cathode to the anode? And that potential difference between the cathode and anode is called the electromotive force of the cell. We discussed in detail in the last period. So particularly I have given how to represent an electrochemical cell. So because we are going to take two off cells, oxidation off cell should be written the left hand side, reduction off cell should be written the right hand side, and these two electrodes linked with a salt bridge to vertical line indicates the salt bridge. In any electrochemical cell, remember the current flows from cathode to the anode. And even I have given the Nernst equation. So various forms of Nernst equation to get single electrode potential or cell potential, even the equilibrium constant, even the work done or the free energy. Because in this the electrochemical cell, so work is done at the cost of the free energy. The free energy decreases. If we calculate the free energy, we can know how much work done can be calculated. I give the various mathematical equations. Today, I will start with how to determine the standard electrode potential of any given electrode. I define both single electrode potential, standard electrode potential. So, single electrode potential means take any metal rod, dip into a metallic salt solution, containing its own ions at any given concentration, at any given temperature. We call it as a single electrode potential. If it is a standard electrode potential means the metal rod should be dipped into a metallic salt solution of 1 molar concentration at 25 degrees centigrade, 1 at passing pressure, other 298 Kelvin, 101.8 kilopascal pressure. The potential thus developed is called the standard electrode potential. So today I will explain you how to measure the standard electrode potential, because I discussed yesterday the reference electrode. Single electrode potential cannot be measured directly experimentally. We require one electrode of more potential. We call it the standard hydrogen electrode. I give another example. How we know the height of the mountains are measured. We take sea level as 0 and height of the mountains are measured. Similarly, so this standard electrode has been constructed, and we don't know what is the potential developed. The potential developed with the hydrogen electrode is arbitrarily taken as 0. Using this as a standard, this electrode can be used to measure the standard electrode potential of any given electrode. I will explain experimentally how we can measure the standard electrode potential of any given electrode. Look at this diagram. Say I have taken, so this is the zinc electrode I have taken. Zinc electrode is the zinc rod dipped into the Zn2 plus ions with zinc sulfate solution. I maintain the 1 molar concentration and 25 degree 1 atmospheric pressure. So zinc electrode has been constructed. Now you have to measure the potential, because the zinc rod Zn2 plus ion, the electrical double layer takes place and the potential is developed. How much potential developed? So I told you it can't be measured directly. We are going to use another electrode, reference electrode, we call standard hydrogen electrode. Already I gave the construction. It consisting of an inner glass tube. So this is a bright platinum foil coated with platinum black is fused to the copper wire. So this is the inner tube served the outer tube. There is a side tube to pass the hydrogen gas at 1 passing pressure, and this was the platinum foil or this electrode dipped into 1 molar hydrochloric acid solution. Already I given the working of hydrogen electrode and even the construction working I explained in detail in the last period. Once again I repeated the construction. So this is inner glass tube. is a bright platinum foil coated with platinum black, is fused to the copper wire. So inner glass tube is surrounded with the outer glass tube. So this is a sided tube. So to which hydrogen gas exactly at 1 atmosphere pressure is bubbled through the solution. And this electrode is dipped into 1 molar hydrochloric acid solution. I told you. So here also the electrochemical takes place and the potential has been developed. How much potential we don't know. So we have taken arbitrarily the potential of this electrode is taken as 0. We have taken the E naught of H2 is taken as 0. So this is a standard electrode is used as a reference electrode. But I have taken the zinc electrode I have taken whose potential has to be measured. So I have taken the hydrogen electrode. So these two off cells are connected internally by using a salt bit. This is a salt bit. I get internal contact with the two off cell and externally so connected here to the potentiometer. And you measure the electromotive force of this EMF of the cell has been determined experimentally. If you determined experimentally, what EMF of the cell was found to be 0.76 volts. But you have taken the unknown electrode whose potential is to be determined is taken. So combined with the standard hydrogen electrode whose potential is known for us, and we constructed an electrochemical cell, and thereby so EMF of the cell has been determined experimentally, and EMF of the cell was found to be 0.76 volts. So at the same time, you must know what is the direction of the flow of current, because I have taken the zinc electrode and hydrogen electrode. I don't know which acts as cathode, which acts as anode. I have to assign the charge in the electrode. To assign the charge in the electrode, you find out what is the direction of flow of current. In this case, so current was found to be flowing from hydrogen electrode to the zinc electrode. I told you the electrochemical cell, current flows from the cathode to the anode. Therefore, the current flow, this is the direction of flow of current. Current flows from hydrogen electrode to the zinc electrode. Thereby, hydrogen electrode acts as a cathode, zinc electrode acts as an anode. And we measure the electromotive force of a cell. So the EMF of a cell, is given by so the potential difference between the cathode and the E naught of cathode, E minus of anode, E naught of anode. So when there is a flow of current, so hydrogen electrode acts as a cathode because current flowing from the cathode to the anode, hydrogen electrode to the zinc electrode. So this cathode is the hydrogen electrode and anode zinc acts as the anode. And EMF of the cell was found to be 0.76 volts. And you have taken E naught of H2 is taken as 0. Arbitrarily the value of mole potential is taken as 0, but E naught of Zn. So what is the value of E naught of Zn was found to be equal to minus 0.76 volts. So like this so this hydrogen electrode can be used to measure the standard electrode potential of any given electrode can be measured. The basic principle is you construct an electrode whose potential be measured is constructed. So combined with the standard hydrogen electrode, you form electrochemical cell internally using a salt bit, externally with a potentiometer. So measure the EMF of the cell experimentally, and at the same time you note down what is the direction of the flow of current. In this case, current was found to be flowing from the cathode to the anode. So therefore, the hydrogen electrode acts as cathode, zinc electrode acts as anode. Now EMF is defined as the potential difference between cathode and anode. As per the direction flow of current, hydrogen electrode acts as cathode, so zinc electrode acts as anode. You know the potential of electrode is 0, but E naught of Zn. Therefore, the E naught of Zn is standard electrode potential of zinc electrode was found to be minus 0.76 volts. Like this, any electrode has been taken, and his standard potential can be measured using the standard hydrogen electrode as a reference electrode. Look at the equation I given. So this is the zinc always zinc undergoes oxidation. Zinc undergoes oxidation. Zinc solid Zn2 plus 2 electrons oxidation of cell. So this hydrogen 2H plus 2E. So this hydrogen gas undergoes reduction. In the net cell reaction, electrons are produced and consumed. Zinc solid 2H plus. Zinc is oxidized to Zn2 plus, H plus and is reduced to H2. This reduction reaction takes place. So the potential has been developed. And EMF of the cell was found to be 0.76 volts. And by this, take the EMF is the potential difference between the two electrodes. The potential of this electrode was found to be 0.76 volts. I told you whenever if you want to represent the galvanic cell, you have to use a basis sign convention. So oxidation of cell should be written on the left hand side. Or this is the sign convention. Take the zinc rod. This is the dipped into Zn2 plus iron, zinc rod, Zn2 plus iron, salt bridge. So this I have taken simply as standard hydrogen electrode I have taken. So oxidation of cell in the LHS, reduction is in the right hand side. So this short bridge indicates the two vertical line. By using the UPAC sign convention, you have to represent this electrochemical cell oxidation. Zinc undergoes oxidation right on the left hand side. So the reduction, addition electrode acts as a cathode, reduction right hand side. And this is oxidation, reduction. So the cathode and anode is separated by a short bridge. Two vertical line indicates the short bridge, and thereby standard electrode potential of any given electrode can be determined. One example. Okay. I will take other example. Look at this. I will take the determination of standard electrode potential of copper electrode. This zinc I have taken the more active metal because it is placed above the hydrogen electrochemical series. One metal I have taken metal placed below the hydrogen, so it is a less active metal. That taken the so we have to determine the standard electrode potential of the copper electrode using the standard hydrogen electrode as the reference electrode. But again I have taken the copper rod I have taken. Dipped into copper sulfate solution of 1 molar concentration. That means you have to construct the standard electrode. That means any metal rod dipped into metallic salt solution of 1 molar concentration, 25 degree, 100 atmosphere. You construct. I have taken the copper rod and dipped into the copper sulfate solution, Cu2 plus of 1 molar concentration. And what is this potential? You have to measure this potential. And again to measure this potential, I have taken the hydrogen electrode as a reference electrode. I told you standard hydrogen electrode is used as a reference electrode. This is a reversible electrode. This can act as both cathode and anode depending upon the other electrode. I have taken the standard hydrogen electrode. So combine these two by using a salt bridge. Salt bridge, a U-shaped glass tube containing potassium chloride, gives electrical contact between the two options and extend it to a potential beta. So measure the EMF electromotive force of the cell has to be measured. I have taken the copper electrode whose potential is to be measured is constructed, which is coupled with the standard hydrogen electrode whose potential is known for us, is a reference electrode. You form one electrochemical cell internally to a salt bridge, externally to a potentiometer. So measure the electromotive force of a cell. But the electromotive force of a cell was found to be 0.34 volts. As I told you, now assign the charge of the electrode. I have taken the copper electrode, hydrogen electrode, which acts as cathode, which acts as anode, because the EMF is the potential difference between cathode and anode. Only by seeing the direction of flow of current, you current and voltmeter, see the direction of flow of current. In this particular case, so current of this is the current was found to be moving towards this is the flow of current. The current was found to be moving from the copper electrode to the hydrogen electrode. Thereby the copper electrode acts as cathode, and this is the hydrogen electrode acts as the anode. To assign the charge of the electrode, you must see the direction of flow of current. In any electrochemical cell, the current was found to be flowing from the cathode to the anode. In this particular cell, the current was found to be flowing from the copper electrode to the hydrogen electrode. Thereby, copper acts as cathode and zinc acts as the anode. But EMF of the cell is given by the potential difference between the cathode and the anode. By looking at the direction flow of current, so the copper electrode acts as the cathode, hydrogen electrode acts as the anode. So EMF of the cell was found to be 0.34 volts. So E naught of copper you have to find out. The potential of hydrogen electrode is taken as 0. Taken already is a standard value taken as 0. Therefore, what is E naught of copper was found to be plus 0.34 volts. So like this, we can measure the standard electrode potential of any given electrode can be calculated. As told you again, you have to go for APC same convention to represent the electrochemical cell, oxidation of cell. So in this hydrogen is anode is oxidation. So I have taken this is the hydrogen electrode I have taken, oxidation of cell. So this is the hydrogen electrode is in contact with Cu2 plus ion, is in contact with copper. This is hydrogen electrode, Cu2 plus ion is in contact. So oxidation of cell in the LHS left hand side, reduction is in the right hand side. This is the LHS electrode, RHS electrode. Oxidation occurs anode, reduction occurs the cathode. So EMF is the potential difference between the cathode and the anode. So diagram I have written. So first copper I have taken, hydrogen electrode I have taken. By the direction of flow of current, we can know the copper acts as the cathode and hydrogen acts as the anode. But if you want to represent the electrochemical cell, oxidation of cells should be written on the left hand side. Reduction of cells should be written on the right hand side. So this is the EMF is the potential difference between the cathode and the anode. You know this potential is 0. You know the EMF. So unknown electrode potential was find out. This was found to be equal to plus 0.34 volts. So like this, I can do example. You can take any metal any element which is contact with its own ions, you can construct, and we can measure the standard electrode potential using the hydrogen electrode as a reference electrode. I told you the last period also. So this single electrode potential cannot be measured experimentally directly. So to measure, we require one reference electrode of known potential. For that, you have taken the reference electrode, where hydrogen electrode is used as a reference electrode. So here you must know all the conditions. So we are passing the hydrogen gas exactly at 1 atmosphere. So this electrode is limited to 1 molar concentration. So this is the hydrogen gas is absorbed in the platinum, is in contact with H plus ion. So this is the hydrogen gas is in contact with H plus ions in this solution. The potential arises. We don't know how much potential arises. I told you it's already taken as 0. It's a reference electrode whose value is taken as 0. Using this, the reference electrode, hydrogen electrode. So the you can construct an electrochemical cell, and the unknown electrode potential can be determined. You take any electrode of unknown potential is constructed, is coupled with the standard hydrogen electrode as a reference electrode. So give internally through a short bridge, externally through a potentiometer. So measure the electromotive force of the cell. You got the MF value. Only thing is you have to assign the charge in the electrode, because just constructing an electrochemical cell, I don't know which is cathode, which is anode. See the direction of flow of current. Current flows from cathode to anode. Looking at the direction of flow of current, so you can assign the charge. In this particular against copper, so this becomes anode. Hydrogen electrode becomes anode. With reference, the zinc electrode, so this becomes cathode. So this hydrogen electrode is a reversible electrode. Depending upon the activity of other electrode, it can act as an anode or it can act as a cathode. It is a reversible electrode. Here the hydrogen electrode acts as a cathode, undergoes reduction. Same hydrogen electrode undergoes oxidation for the anode, depending upon other activity. So this the reference electrode, hydrogen electrode, is used as a reference electrode to measure the unknown electrode potential. Okay, my dear students, I hope you can understand. So this is the basic principle. Any electrode whose potential is to be measured is constructed. It is combined or coupled with the standard hydrogen electrode whose potential is known for us. So connect internally through a short bridge, externally through a potentiometer. You measure the EMF of the cell experimentally. That's experimental work. But you have to assign the charge on the electrode. So for that you see the direction of flow of current. Always current is flowing from the cathode to the anode. Then EMF is the potential difference between the cathode and the anode. So assign the charge in this electrode. So you know the EMF value, but unknown potential can be calculated. But here in this electrode, hydrogen. So this acts as anode, H2, 2H plus 2 electrons. This oxidation of cell. So the copper undergoes reduction, Cu2 plus. What is the Cu2 plus? So 1 molar concentration have taken. So this is undergoes reduction. The copper is deposited. So this undergoes oxidation. This undergoes reduction. In the net cell reaction, 2 electrons are produced and consumed. So the hydrogen Cu2 plus. For Cu2 plus, so this hydrogen is reduced to H plus ion. Cu2 plus so get reduced to copper. So this redox reaction takes place, and chemical energy becomes electrical energy, and this is found to be equal to 0.34 volts. By knowing this EMF of the cell, knowing this potential or known potential can be calculated. I told you what E naught of C to find out. So this value is known for us. We can start with 0. EMF is known for us. By these two values, unknown potential can be calculated experimentally. But if at all you prepare the board examination, you have to write the diagram, you have to write the electrode reaction, off cell reaction and net cell reaction. You have to represent this electrochemical series as per UP's same convention. Then take EMF value. What EMF is the potential difference between the cathode and the anode. Assign the charge which is cathode, which is anode by the direction of flow of current. So knowing the EMF, knowing this potential is 0, unknown standard electrode potential can be determined. Now two examples I have given. So here I have taken the hydrogen electrode as a reference electrode. One case it acts as a cathode, other case it acts as an anode. It's reversible electrode. Depending upon the activity, zinc is more active. Towards more active, this becomes cathode. So because less active, this becomes anode. This reversible electrode, it can act as a cathode, or it can undergo oxidation or reduction. Using this reversible standard hydrogen electrode, so the standard electrode potential of any given electrode can be calculated. I hope you can understand this, the measurement. Okay. With this, okay, student friends. Now I explain you how to measure the standard electrode potential of any given electrode using standard hydrogen electrode as a reference electrode. Now, you measure the standard electrode potential of all elements. And what I will do is, I will arrange them in the increasing order of their standard electrode potential. The resulting series is called the electrochemical series. So this electron is a electrochemical series. So this electrochemical series you have also studied in first year, and this become more useful in second year. Lot of the multiple choice questions. So this data is required. So try to follow me and try to understand the various principles of electrochemical series. That is by using the standard hydrogen electrode, and we measure the standard electrode potential of all the electrodes, and we measure them in the increasing order of the standard electrode potential. The resulting series is called electrochemical series. The elements are arranged in the increasing order of their standard electrode potential on the hydrogen scale. We will take a hydrogen as 0 on the hydrogen scale. So this minus 3, minus 2, minus 2, minus 1, it becomes 0, then plus increasing order. If the elements are arranged in the increasing order of their standard electrode potential on the hydrogen scale is called as the electrochemical series. So in different forms you could able to use this electrochemical series. Data will be given to you in the examination. Potential will be given to you. How to correlate for various the prediction, you could able to application of point there. Or here I told you, these elements are taken the lithium plus base metal rod, lithium rod dipped into unit molar concentration of lithium at 25 degree 1 atmosphere. So standard electrode is constructed of lithium, and ignition electrode potential is measured is -3. Like these all the elements. So the standard electrode potential is measured assuming the hydrogen as 0, and they are arranged in the increasing order of the standard electrode potential, and this series is called the electrochemical series. Look at this. So this is this is less potential, and the potential goes on increases. So this is the negative potential, this is positive potential. So negative potential S0 means it is anode, the electrochemical cell is anode. The positive means cathode. So negative anode means they got more tendency to lose electron, means they are more reactive. So this thing, that is you can say, if you move from top to bottom the electrochemical series, as the potential increases, activity increases. Because lesser the potential, more will be the activity. This is -3, so this is -2. Among these two, minus is a lesser value. Lithium is more active than potassium. You interpret different way. I'll give the general way of representation. But as the potential keep on increases, activity increases. Or I put it in a very rough manner. The metal placed, take the hydrogen now. So metal placed above the hydrogen, they are more reactive. Metal placed below the hydrogen, they are less reactive, because they got the positive, higher the potential, lesser will be the activity, or lesser the potential, more will be the activity. So by this one simple concept, we can correlate any properties predicting the electrochemical series. As I told you, so these elements are arranged in the increasing order of their standard electrode potential on the hydrogen scale, which is taken as 0, and it is called the electrochemical cell, electrochemical series. And these, as I told you, so the less potential is more activity. As the potential keep on increases, activity decreases. Because as per the table, highly reactive lithium, least as per this table. Some example I will take. Copper is less reactive, plus 1.5. So this is the more the potential, less will be the activity, or less the potential, more will be the activity. Or you can say the metal placed above the hydrogen, they are more reactive, but metal placed below the hydrogen, they are less reactive. By using this concept, we can predict the feasibility of a chemical reaction. I'll give some simple example. Say I will take one metal placed above the hydrogen. Say I will take the example zinc. I will take. So zinc is the metal placed above the hydrogen. I will take one metallic salt solution of metal placed below the hydrogen. I will take copper. So I will take copper sulfate. I will take copper sulfate. Look at this example. The metal placed above the hydrogen, whose potential is -0. This are taken, whose potential is -0.76 volts. So this is the more reactive. And I have taken the copper, the metal placed below that is a copper salt I have taken, CSO4 I have taken. This is plus 0.34 volts. So this is more potential, less reactivity. So zinc, I have taken the metal placed above the hydrogen. One metallic solution placed below the hydrogen. Guess what will happen? But zinc displaces copper. So we have the copper plus zinc sulfate is formed. Look at the example. So zinc displaces copper from copper sulfate solution. Why zinc displaces copper? Because zinc is more reactive. Your zinc is placed is potential 0.76 volts more reactive than copper 0.34 volts. Or you can say zinc is placed above the hydrogen more reactive. Copper is placed below the hydrogen less reactive. Zinc being more reactive displaces copper from the copper sulfate solution. We can discuss now the feasibility of a chemical reaction. So, the real example, I will take one metal placed below the hydrogen. I will take copper. Okay. So, this is copper. Okay. I will take the metallic salt solution of the metal placed above the hydrogen. I will take same example. I will take zinc sulfate. I will take. Okay, so what happens? You got this equation. Here they don't say the copper. The copper. The copper cannot displace us zinc from zinc sulfate solution. So that is no reaction occurs. But I will give the reason. Because the copper is placed below the hydrogen is potential 0.34 volts, but zinc is placed above hydrogen minus 0.76 volts. So copper, so having high value is less reactive. So copper being less reactive, it cannot displace us more reactive zinc from zinc sulfate solution. So we can predict the feasibility of a chemical reaction. In generally, so the metal placed above the hydrogen, they can displace us the metal from the metallic salt solution or the metal placed below the hydrogen. But the metal placed below the hydrogen, they cannot displace us the metal placed above the hydrogen because they are the negative potential, more reactive, less reactive. More reactive can displace us the less reactive metals. Being less reactive, they cannot displace us the more reactive. The feasibility of a chemical reaction can be explained with the electrochemicals. It's a very important data. How this data can be used in a different way, we discuss while discussing your national entrance examination multiple choice questions, which will come to later. But here so as slowly as the potential keep on increases, activity increases. But again, the example of zinc they have taken. Zinc displaces copper from copper sulfate solution, but copper cannot displace zinc from zinc sulfate solution. Zinc being more reactive, so can displace the copper from the copper sulfate solution. Copper being less reactive, it cannot displace zinc from the zinc sulfate solution. One feasibility can be predicted. Other example I will give. Say I will take example of zinc. Well, I will take the example. Say zinc. Or take dilute H2SO4. So this is dilute H2SO4. Dilute H2SO4. Okay, so what will happen? So zinc. So this is zinc sulfate. Or zinc sulfate is formed, and hydrogen gas is liberated. But here zinc displaces hydrogen from dilute acid. So zinc displaces hydrogen. So because zinc is minus 0.76, highly reactive, but hydrogen is 0, less reactive. Zinc being more reactive displaces the less reactive hydrogen from dilute acid. Including zinc displaces hydrogen from dilute acid. But other examples of take copper, copper Cu. Or take dilute H2SO4, or take dilute H2SO4. Hence what will happen? Don't say no reaction. Reaction occurs. Copper dissolves in sulfuric gas in the presence of air to form copper sulfate, but no hydrogen gas is liberated. No H2 is liberated. No H2 is liberated. That means the copper being less reactive, it cannot displace hydrogen from dilute acid. But in generally, the metal placed above the hydrogen, they displaces hydrogen from dilute acids. But the metal placed below the hydrogen, they cannot displace hydrogen from the dilute acids. So I told you activity. As the potential increases, but activity decreases. So this way, all the metal placed above the hydrogen, they are more reactive. So when compared to 0, less reactive. So these metals can displace hydrogen from dilute acids. But they like copper, silver, gold. So they are the positive electron potential, less reactive. Being less reactive, they cannot displace hydrogen from dilute acid. Just take the example, zinc minus 0.76. So more reactive can displace hydrogen from dilute acids. The same copper less reactive, so cannot displace the more reactive hydrogen. In generally, all the metal placed above the hydrogen, they can displace hydrogen from dilute acids. But metal placed below the hydrogen, they cannot displace hydrogen from the dilute acids. But some of the feasibility of a chemical reaction can be studied with this electrochemical series. Somehow, illustrations I will give. Some illustrations I will take. So the other thing is the most important is very important for entrance exam point of view. So the elements, so the metal placed above the electrochemical series. Say the lithium has got more tendency to lose minus the very low value of electropotential, more tendency to oxidation, more tendency to lose electron. Elements placed at the top of the electrochemical series have got more tendency to lose electron, means they are very good reducing agents. They are very good reducing agents. So this, if you go from reducing power K bond increases, you move from top to bottom of the electrochemical series. Look at this. So elements placed at the top of the electrochemical series have got more tendency to lose electrons. Means they are very good reducing agents. Lithium is a very good reducing agent. And this so this the reducing property from K bond increases as you move from top to bottom in the electrochemical series. Or if you want to express in terms of this electropotential, lesser the value of electropotential, greater the reducing power. Or greater the value of electropotential, lesser will be the reducing power. Because the entrance examination, the values will be given to you. You have to use the data which is a strong reducing power, which has got the least reducing power. This to lesser the potential, greater is the reducing power. So greater the potential, lesser is the reducing power. Therefore, so elements at the top of the series has got more tendency to lose electron. They are very good reducing agents. As you move from the potential increases, reducing property also keep on increasing. The keep on is a decreasing reducing power. If you move from top to bottom in the electrochemical series, reducing power decreases. But if you want to express in terms of its value, lesser the value of the electrode potential, greater is the reducing power. So greater the value of electrode potential, lesser will be the reducing power. So you can see from top to bottom, I have written into decreasing reducing power. If you move from top to bottom in the electrochemical series, reducing power decreases. One concept. Other will be, so elements at the top of the series now, they have got more tendency to lose electrons. They are very good reducing agents. Or you can say they are poor oxidizing power. They are very good reducing agent. They have got poor oxidizing power. If you move from top to bottom in the electrochemical series, so increases the oxidizing power will be increases. They are very good reducing agents, but they are poor oxidizing power. But if you move from top to bottom in the electrochemical series, so the oxidizing power will be increases. Or if you want to express the oxidizing power in terms of the standard electrode potential, you can say directly, lesser the electrode potential is, less is the power of oxidation. So greater the value of standard reduction potential, so greater is the oxidation power. If this is reducing power become inversely, but oxidation power will directly. So lesser the value, lesser the oxidation power. So more the value, more the oxidation power. That is the increasing oxidation power. If you move from top to bottom in the electrochemical series, so it increases the oxidation power. If you move from top to bottom in the electrochemical series, decreases the reducing power. Usually in all your entrance examination, so the standard electropotential data will be given to you. You have to choose which is a stronger reducing power, which is a stronger oxidizing power. You term in terms of the standard electrode potential. So the reducing power, you take the values are inversely proportional. Lesser the electrode potential, stronger is the reducing power. Or greater the value of reduction potential, so weaker will be the reducing power. But if you want to express oxidation power, take directly proportional. Lesser the value, lesser the oxidation power. So greater the value, greater is the oxidation power. So such properties can be predicted with the help of the electrochemical series. The other application. So one more application say if you want to construct a galvanic cell, I want to know the standard EMF of this cell. So I told you to construct an EMF electrochemical cell, you have to choose elements of different reactivity. You cannot choose the reactivity of same reactivity. You can take metals of different reactivity. Normally, if we take, to construct galvanic cell, I have taken zinc electrode, I have taken zinc electrode, I have taken copper electrode, I have taken this negative potential, undergoes oxidation, this undergoes reduction. You can take up, the EMF is the potential difference between the cathode and anode. With this electrochemical series data, we can calculate the standard EMF of the cell. So, don't mean that EMF of the cell, you have taken only the negative potential and the positive potential. So, any two we can use. Suppose I will take sodium and magnesium, I will form an electrochemical cell. So, lesser potential become anode, here more potential become cathode. current flows from cathode to the anode. We can take any elements differing in the activity, out of which relatively lesser potential electrode become anode, it undergoes oxidation. So greater becomes cathode, undergoes reduction, redox reaction takes place. Only difference is if you take a small difference in the electrode potential, smaller will be the EMF lesson. If we choose elements of greater electrode potential difference, so greater will be the EMF of the cell. If you want to get a greater EMF value, we will choose the electrode having a large difference in the standard electrode potential. Lesser the potential is lesser will be the EMF. More difference means more will be the EMF of any galvanic cell can be constructed with the two electrodes, and standard EMF is E, we call it E naught of cell. Standard EMF of the cell is called E naught of cell, can be measured by using the electrochemical series data. Other application. We'll go to one more last application. Some elements, they are found in the earth crust in the free state. Take example of copper, silver, gold. They are found in nature in free state. The copper occurs as copper in the earth crust, or silver, gold, they occurs in the earth crust. Why? Because they got high value of electrode potential, less reactive. That's why they are found in the nature in the free state. Take example of alkali, lithium, potassium, barium, calcium. They are not found in nature in the free state in the earth crust. They are distributed in different form like oxide form, halide form, carbonate form. So in different way, in the earth crust, they combine the different elements. So because of more activity, they are found in the nature in the combined form because of the more reactivity. That's what the basic concept is. So as the potential increases, activity decreases. That is the, or I can take the hydrogen is taken as a scale 0. The metal based below the hydrogen, they are more reactive, but metal based below the hydrogen, they are less. Or you can say, so the activity will keep on decreases as the potential increases. But various application, so you will be able to apply the application of your mind in solving the number of numericals in your national competitive examination. This you are taught in first year also. We are going to taught in second year also. This is the electrochemical series. It is the, so using the standard hydrogen electrode, we measure this, the standard electrode potential of all the electrodes. They are arranged in the increasing order of the standard electrode potential on the hydrogen scale. Why we call it hydrogen scale? Because we have taken hydrogen electrode whose potential is 0. Using it 0 as a relative, you measure the electrode potential, arranged in the increasing order of the electrode potential. So this is called the electrochemical series. So all these the properties of visibility of the reaction can be predicted with the help of the electrochemical series. Okay, friends, understand? Friends, again I am going to continue the electrochemical series, and I discussed the formation of the galvanic cell, and we discussed the application of the electrochemical series. Now I will come to the last bit in this electrochemistry, what is corrosion, and we have to explain the electrochemical theory of corrosion. Corrosion is rusting. That is, you have to define scientifically what is a corrosion. Corrosion is the destruction or deterioration of metals and alloys under the influence of natural or industrial environment is called as corrosion. We take iron as example. Iron undergoes corrosion. On the surface, a reddish bone powder is formed. That's called rusting. Is called the corrosion. Or more interestingly, corrosion is called as the reverse process of metallurgy. Imagine, is a reverse process of metallurgy. Suppose I take hematite, Fe2O3. Hematite is Fe2O3, hydrated Fe2O3, 3H2O. So hematite. I do a lot of metallurgical operation. I convert it to iron. But iron has got a tendency to go back to its original state, Fe2O3, 3H2O. Is a reverse process of metallurgy is called as corrosion. So we take hematite as iron ore occurs in nature. We do a lot of chemical operation and we do manufacture iron. But iron has got a tendency to go back to its original state, Fe2O3, 3H2O. So the reddish brown powder, that is the reverse process of metallurgy is also called the corrosion. But corrosion scientifically defined as destruction of metals and alloys under the influence of industrial or natural environment is called as corrosion. So interestingly, the corrosion is an electrochemical phenomenon. But corrosion is an electrochemical phenomenon. Electrochemical phenomenon means, I explained the galvanic cell, You go back, imagine how you have taken a galvanic cell, I have taken a zinc rod, dipped into zinc sulfate solution. Copper rod, dipped into copper sulfate solution. Zinc is more active, becomes anode. copper, less reactive reduction, it becomes a cathode. We connect internally using a short bridge, actually through a copper wire. Current flows from cathode to the anode. In the laboratory, today galvanic cell has been constructed and chemical energy has been converted into electrical energy. In nature, so this galvanic cell will takes place, formation of galvanic cell takes place during the rusting process. That is how this is called electrochemical theory. In the nature, so how suppose I will take a piece of iron. The piece of iron when it exposed to a moist air, it undergoes corrosion. There in iron, imagine iron atom. Iron atom is so the more reactive. Is placed above the electrochemical series. This has got tendency to lose electron. So this becomes anode. And this iron contains any lots of impurity atoms. Say it contains a small amount of copper as an impurity. So that copper becomes the cathode. Iron atom and impurity atom. There is a galvanic cell formation. And you are going a salt bridge in the nature. Then where is a salt bridge? Atmospheric moisture acts as a salt bridge. And in the electrochemical cell, we use a copper wire, the electrons will flow from anode to cathode. Here, and the body of the metal, the electrons will flow from anode to the cathode. In the nature, we developed a galvanic cell in the laboratory, chemical reaction has been taken, reversible redox reaction, and that chemical energy has been converted into electrical energy and unified a galvanic cell. In the nature, when a metal undergoes corrosion, large number of small galvanic cell will be set up. And more active metal, anode undergoes corrosion. See, remember, in any metal, anodic part undergoes corrosion. Cathodic part will not undergo reduction. Only the substance is more reactive metal, which has got more tendency to lose electron, which becomes anode. They dissolve, they undergoes the corrosion. Remember, anodic part is more susceptible for oxidation than the cathodic part. If you take the iron as an example, I will tell you, iron atom is acts as an anode. And any impurity atom, less reactive impurity atom acts as the cathode. Atmospheric moisture acts as the electrolyte. And the body of the metal serves as a source for the flow of electrons. Electrons will flow from anode to the cathode. Similarly, so ions will move with the atmospheric moisture is the electrolyte. More active metal dissolves, undergoes corrosion. So that corrosion spreads to the entire metal. The metal will get corroded. It is called the electrochemical theory of corrosion. You can understand the principle I am giving. By taking the iron as an example, you would explain how the iron undergoes corrosion. I have taken the iron. Finally, iron, it forms a rusting of iron. It forms hydrated ferric oxide, the hematite composition. The reddish brown powder is formed. That is called rusting of iron. It is purely an electrochemical phenomenon. I will support with all these suitable equations. So the rusting of iron is purely an electrochemical phenomenon. Look at this diagram. I defined the corrosion is the destruction of metals and alloys under the influence of natural or industrial environment is called the corrosion. Metal will get corroded, destruction of metal will take place, or deterioration of metal will take place is called the corrosion. Now we will state by taking iron as an example, how a commercial iron when exposed to air undergoes corrosion. It is purely an electrochemical phenomenon. Not one or two, large number of tiny small galvanic cell will be set up. More active iron dissolves undergoes the corrosion. Look here, I have taken a piece of iron. This is exposed to the moist air. See, I have taken anodic part. I have taken an iron atom. So iron atom is more active. It becomes anode. I have taken the anodic part. I have taken. But any impurity atom, it may contain any impurity like copper, even iron contains silver also, even iron contains gold also. So there is the impurity atom acts as the cathode. So the anode and the cathode. So the the anode, so the iron the more tendency to lose electron at anode. Iron dissolves to form a Fe2 plus 2 electrons. Iron undergoes oxidation. Here the iron undergoes oxidation, a Fe2 plus 2 electrons. What are these 2 electrons? These 2 electrons on the body of the metal moves to the cathodic area. How the reaction supposed to be taking place? You don't require wire for connection. So they have taken the iron atom more active. It dissolves. It undergoes oxidation. So this Fe2 plus and electrons are released. On the body of the metal, these electrons are traveling to the cathodic area. What happens in the cathodic area? In the cathodic area, atmospheric moisture in the presence of air or oxygen takes up these electrons, 4 electrons hydroxyl ions are discharged at the cathode. Even the water directly undergoes reduction by accepting 2 electrons, decomposes the hydroxyl and hydrogen. So this hydrogen goes to the atmosphere. What is the hydroxyl ions? So these hydroxyl ions are discharged at the cathodic area. So these hydroxyl ions, this is moisture, atmospheric moisture, with the help of the moisture. So this OH minus ion will traveling towards the Fe2 plus ion. So Fe2, this OH minus ion is going towards the Fe2 plus ion. So this Fe2 plus ions takes up OH minus ion, ferrous hydroxide is formed. So this ferrous hydroxide, in the presence of moisture and oxygen, ferric hydroxide is formed. And this ferric hydroxide, so finally decomposes into hydrated ferric oxide, reddish brown powder, rustic is formed, is purely an electrochemical. How interesting we can see. Is a commercial piece of iron, when exposed to air, undergoes the corrosion. There the more active iron acts as anode. And iron is not possible to prepare in 100% pure metal except silicon and germanium for semiconductor devices we prepare. None of the metal can be purified by 100%. It contains impurity atom. So less reactive. I give the electrochemical cell. A small difference in electrode potential become anode and cathode. So here the iron becomes anode. Any less reactive impurity atom becomes the cathode. Between the anode and cathode, so wherever iron atom and impurity atom, there is a galvanic cell formation. Large number of small, tiny galvanic cell will be set up. More active iron dissolves, undergoes corrosion, that spreads the entire metal, and the metal will get corroded. Look at the equation. Iron, so means the more active iron, I thought the anodic part means it acts as an anode. At anode, oxidation, Fe2 plus, iron dissolves to form Fe2 plus and electrons, undergoes oxidation, iron dissolves. So this is Fe dissolves in Fe2 plus. What happens? These electrons. So these electrons move on the body of the metal to the cathodic area. In the cathodic area, hydroxyl ions are discharged. Look at the cathodic area, atmospheric moisture in the presence of air. So takes up these electrons, hydroxyl ions are discharged. One reaction. Number of reactions will take place. I give you such a reaction. Even the moisture directly can take up the electrons. So it decomposes to hydroxyl ions. Hydrogen gas is formed that will discharge in the atmosphere. What I want is the hydroxyl ions are produced. So this is the at cathode, hydroxyl ions are discharged. So these hydroxyl ions, with the help of the atmospheric moisture as an electrolyte, they attracted towards the Fe2 plus ion. Attracts these OH minus atom traveling from cathodic area again to the anode. Naturally the process taking place. So this Fe2 plus ion reacts with the hydroxyl ions to form the ferrous hydroxide. Ferrous is unstable. It had to go to the ferric state. So this ferrous hydroxide again with moisture in the presence of air, the ferric hydroxide is formed. And this ferric hydroxide finally decomposes to Fe2O3 3H2O, so reddish brown powder, rustic apparent. That's why I told you. So the corrosion is a reverse process of metallurgy. But you have taken the iron has been manufactured. Iron again goes back to original state is Fe2. This is a composition of hematite. From hematite you manufacture the iron. Iron again has a tendency to come back to the original state, hematite form. So this is the beauty of electrochemical phenomena. How we discuss the galvanic cell formation now. Same in the nature. Large number of tiny small galvanic cell will be set up. More active iron dissolves, which undergoes the corrosion. I will repeat the basic principle. See the electrochemical theory of corrosion. But more active iron becomes anode. Less active impurity atom becomes the cathode. Atmospheric moisture acts as the electrolyte. Body of the metal serves as a source for the flow of electrons. So redox reaction takes place naturally. The more active metal undergoes corrosion. Remember always, anodic part undergoes corrosion. This is also multiple choice part. Cathodic part doesn't undergoes oxidation because they more reactive. Tendency to lose electron which become anode, they undergoes the corrosion. Cathodic part doesn't undergoes any corrosion. So iron undergoes purely an electrochemical phenomenon. Can you follow? Okay. Again repeat here. Then so this is the corrosion is purely an electrochemical phenomenon. So iron undergoes corrosion. or you take any more your number of metals were given, if they have got the negative electroporation, they undergoes corrosion. So what are the methods employed to prevent the corrosion? So corrosion can be prevented because the metals are used in various parts, especially in automobiles, household construction, in the building construction. We have to protect from corrosion. How the corrosion can be prevented? But again, the four important methods are given. So corrosion can be prevented by painting, by applying oil or grease, by electroplating, by galvanization, and cathodic production. So these 5 general methods are employed to prevent the corrosion. I'll explain briefly. So painting, normally you have seen. So we apply the paint because if it is iron rod in the construction windows, iron undergoes corrosion. Normally we go for painting. We apply the paint. So it avoids the contact of atmospheric moisture and air, and thereby the galvanization formation can be prevented and corrosion can be prevented. Most of the metals and alloys are prevented corrosion by painting. Painting is done not for decoration purpose, but technically for the prevention of corrosion to carry out the painting. By applying oil or grease. For the metal, you put oil or grease. If you put the oil or grease, what happens? Atmospheric moisture cannot come in contact with the metal. There is no chance of formation of the galvanic cell, and because the corrosion can be prevented by applying the oil or grease on the metal surface. And that is by electroplating. What is electroplating? Electroplating is a process in which so the superior metals are coated over inferior metal. Some metals does not undergo corrosion, non-corroding metals. So non-corroding metals will be coated over corroding metals. Or we call it the non-corroding means they are superior metals who are coated over inferior metal. Suppose in most of the automobiles, they take iron. Iron undergoes corrosion. They do chromium plating, nickel plating by simple electrolysis. So a thin layer of the nickel or the chromium can be plated over iron to prevent corrosion is called the electroplating. Electroplating is a chemical process in which the coating the inferior, superior metals over the inferior metal. Take iron as an example, which is more susceptible for iron oxidation, which easily undergoes corrosion. But take the example nickel and chromium. They are not easily undergoes corrosion, they are not corroding. So the thin layer of nickel or chromium can be plated over the iron is called electroplating technique. The corrosion can be prevented. Other is called as the galvanization. Most of the nuts, bolt, all things we can see they have the galvanization. What is galvanization? So galvanization is the process of coating the zinc over iron. We take zinc is coated over, so gives a decorative coating. Zinc can be coated over iron. As zinc is more active. It undergoes oxidation, and a thin layer of oxide layer, protective oxide layer is formed, and then it protects the iron from corrosion. It is called galvanization. Coating zinc over iron. Zinc is more reactive than iron. Zinc, the zinc undergoes oxidation and protects iron from corrosion. Zinc forms zinc oxide, a inner layer. That inner layer protects the iron from corrosion, and that is called galvanization. The process of coating zinc over iron is called the galvanization. For cathodic production, I told in the electrochemical cell formation, anodic part undergoes corrosion. Cathodic part does not undergo corrosion. If you want to make the corrosion prevention, you make the article as cathode. Normally, this is done in underground iron pipes. So in the water or sewage carrying, they put iron pipes in the underground. What they do, because iron undergoes corrosion, is a negative, easily undergoes oxidation. What do? They connect a magnesium. So magnesium is more active. Magnesium becomes anode and makes the iron cathode. So because the cathodic can be prevented by corrosion, putting cathodic corrosion. Normally done in the underground, putting the pipes, iron pipes. They here and there they connect the magnesium in the underground. Magnesium becomes anode, and the iron becomes the iron pipe becomes the cathode. It can protect from corrosion. So all these methods are applied for the prevention of the corrosion, like the painting, applying oil or grease, by electroplating, plating nickel or chromium over the iron, galvanization, coating zinc over the iron, the cathodic particle. If you want to prevent corrosion, you make it a cathode. So cathode doesn't undergo corrosion. It's called a cathodic production. Number of methods are employed to prevent the corrosion. Friends, So this completes now the electrochemistry, and only numericals you have to solve, odd number of numericals you have to solve. So these all the numericals will be solved in the classroom, because in the presentation I cannot solve the problems. You be ready with this all the basic principles before coming to the class. You study. We give some assignment. You work out all the assignment. Come to the classroom. Then we can take the number of numericals on the concept of the electrochemistry. It's a very interesting chapter. Lot of application. Number of questions will appear in a national competitive examination. First, before coming to the class, you please go through all this. Study. You put a video. You see 1 time, 2 times, 3 times. You view several times till you become clear. Refer your NCERT book. Make it thorough with these the basic concept and come to the class. Okay, students. Thank you very much.
Subscribe now and press the bell icon. Never miss an update.